Okay. Good evening, everyone. I'm Barbara Long. I'm a Vice President at the Aquarium of the Pacific. Thank you for coming here and joining us tonight. This is the second in a three-part series on California and climate change and water. Tonight we have Jeanine Jones, who was also here last week, and Mike Anderson. So this is tonight, climate change and what it means to California. We want to thank our series sponsor, our lecture sponsor, the Gazette newspapers. And then let me introduce our two speakers tonight. First, Jeanine Jones will speak to you, and she serves as the California Department of Water Resources Interstate Resources Manager. A civil engineer, she has a background in interstate water negotiations, statewide planning, and drought preparedness. Then Mike Anderson will speak to us. Mike serves as California State Climatologist in the Department of Water Resources. A civil engineer, he has a background in hydroclimate modeling and monitoring and works in the department's flood forecasting section. It is now my pleasure to welcome Jeanine Jones.
What we have planned for you is a presentation where I'll start out and begin with a little bit about how we know what we know about climate change effects on water resources, how we take this information, which is from an emerging area of science and very much in the basic research domain, how we transition that to something that we can use or look at for water management, some of the uncertainties associated with that, knowledge gaps, and things that we would like to know more about. And then Mike will take over and talk about examples of some climate change impacts to specific areas of water management in California. Now, just a word about sort of definitional stuff before I start off. IPCC is a term I'm going to be using a lot tonight. That's the Intergovernmental Panel on Climate Change, a group that was impaneled via the United Nations and the World Meteorological Association. You may have heard of this group because it won the Nobel Peace Prize in 2007 for its work on preparing assessment reports on climate change. Something that is hugely important to be able to do these assessment reports is the ability to do climate models. And you may hear me use the term global climate model, GCM, general circulation model. These all mean the same thing. These hugely complex models that the science community uses to model the atmosphere and its interactions and be able to develop projections of what future climate might look like based on some key assumptions like emissions scenarios, which I'll be talking about a little bit later in this presentation. But these are the estimates of, for example, how much greenhouse gas emissions might people put into the atmosphere in the future. And one of the things that we learn from these climate models, hopefully, is what the science community refers to as detection and attribution. Can you detect that something is going on in the climate system, and can you attribute it either to natural climate variability or to the term the science community often uses is anthropogenic forcing, which in plain English means a human-induced climate change. Now, our presentation tonight is going to be focusing really on the impacts of climate change a lot, but I don't want you to lose sight of the fact that natural climate variability is also hugely important. And in fact, I'll be finishing up my part of the presentation with a couple of thoughts on that aspect. So moving forward now, I'm going to talk about the how do we know what we know, and I'm going to be using the IPCC reports as the example of this. IPCC's first report was published in 1990. These reports attempt to represent the consensus of a broadly based international scientific community, and they have a very structured process that they go through to get to be able to doing their reports, and they are very careful in how they use terminology, and they have defined terms. For example, what does likely mean as opposed to very likely or really, really likely? They didn't use that one, but so they're very careful on their use of terminology. And so this is what they said in their very first report. And if you look at this, this is a pretty mild statement. Yeah, we know the greenhouse effect exists and it keeps Earth warm, this was kind of not too earth-shaking. But what we're going to do is step through the series of their assessment reports and see how much stronger the language gets over time. So let's look at their second assessment report. Key point here, balance of evidence suggests, this is a direct quote, that there's a discernible human influence. Now still, this isn't really strong language. Getting stronger, but still not hugely so. Now, let's come up to 2001, what's called the third assessment report. And now we say in light of new evidence. Well, what new evidence are they talking about? They're talking about the continued science research that was going on in between their second assessment report and this third one. And we say that most of the observed warming, and they say is likely. Notice they just said likely. They didn't say very likely or really, really likely here. We're still just at likely. And that they say that we project that under, going forward, global average temperatures of sea level expected to rise. So this is the 2001 report, but the last one that was published in 2007, the language got quite a bit stronger in terms of their conclusions. So the understanding of anthropogenic warming and influences on climate, and TAR, as they call it, stands for Third Assessment Report. So this is since their 2001 report, they're saying we have a very high confidence. Now that is strong language as they define it. Very high confidence that the net effect of human activities, basically since the Industrial Revolution, has been of warming. Warming of the climate system is unequivocal. That's very strong language. And we can observe it in all of these different phenomena that we can measure, that we can see. And then we say that much of this observed increase is very likely. Notice we've moved from likely to very likely due to observed increase in human-induced greenhouse gas concentrations. And importantly, from an adaptation standpoint, they say that this warming that we're seeing is expected to go on for a substantial period of time, even if you turned off all of the increased emissions today, basically because there's a lot of inertia in the climate system. And I should also say that tonight we're going to be focusing on climate change impacts, not the adaptation side, but dealing with, this long-term effect is very much something that the adaptation side to climate change is concerned about, and that's what we'll talk about in our third series next week. So this is kind of a plug to come back next week for more on tonight will be what we know about the impacts. Next week will be, so what are we doing about the impacts? Kind of the way it breaks down. So now let's talk about how do we get this information, this basic research, a lot of it, a huge percentage of it, maybe not all of it, but a large percentage of it being done in the atmospheric science community. How do we make that actionable in the world of water management? There's a reason for this picture of a bridge on the slide. Many of you have probably heard of the National Academy of Sciences, the National Research Council, which is the premier science organization in the United States. A couple of years ago, they published a report with a very catchy title. They called it Bridging the Valley of Death, the Transition from Research to Applications. And this is not an unusual phenomenon in the science community, and you see it across many disciplines, not just this one, but it points out it's very difficult to take basic research and move it into practice. It does not happen overnight. It's an iterative, long-term process, and in this case, much of the climate science work that's being done is still really in an emerging area of science. So the knowledge is changing as we go along, so to speak, which complicates the ability to say, well, okay, this is the answer, now we can go do something with it. And if you noticed in those nice statements of basic science research from the IPCC reports, you didn't see what we in our world would call something that we could use directly. They didn't, for example, say that, well, by 2100, stream flow in all of the rivers on the West Coast is going to decrease by 15%. Now, that would be a nice, useful statement that we could immediately take and run with and do something with. Well, not so. You have to go a very long way to get from this end of the bridge to our end of the bridge over here, and there's a lot of work involved in doing that. So it's not a simple thing. But when you run that process forward for California, or the United States for that matter, these are some of the typical impacts that I'm sure you've seen mentioned in newspaper articles or in climate blogs on the web or these kind of things. And Mike will be covering some of the specifics of these in his presentation. But these are the kind of impacts that you think about. And our challenge in our world is to try and quantify them, figure out what the uncertainties are, and see how we can take this information from the world of basic science and turn it into something that we can act on. Now, when we talk about uncertainties, there are a whole series of steps that you have to go through to transition this information from the basic science world and put it into terms that we can use, for example, in engineering practice to be able to evaluate the integrity of our water systems or estimate what kind of future water supply conditions or flood conditions that we might be facing. And I'm just going to step through some slides on some of these examples of uncertainty. This slide is actually borrowed from a researcher at the National Center for Atmospheric Research, Jim Hurl, very much in the basic research world, the community that does climate models. Now, I mentioned that these global climate models, or GCMs, well, when the science community builds these GCMs, and there's probably a couple dozen different models out there that different institutions or universities have developed over time, the early phases, or sort of version 1.0 of these models, if you want to think of it that way, will really just focus on the atmosphere. But that was only a small piece of the problem, because the oceans, for example, are really important. We know the oceans are a huge sink for carbon dioxide, for example. And you also have to look what's going on in the terrestrial system, and you have to add in the carbon cycle. So while the early versions of the models really just kind of looked at one layer, so to speak, the later versions of the models get better by including more detail, more information. But these models also have to cover the entire globe, because climate, after all, is a global phenomenon. And the way they do it, for modeling purposes, is they take the surface of the globe and they divide it up into these little cells. They put a grid on it. And in the earliest models, the grid might be a couple of 100 kilometers on a side. Well, okay, so you get 2 grid cells for California. That's not a whole lot of detail. By the time you get to the 2000 assessment report, we at least have a few more grid boxes here for California. But why is the resolution of geography really important for us? Well, think about California, for example. Landforms, i.e. mountain ranges, are hugely important with respect to where precipitation falls and how much of it falls. There's this thing called orographic precipitation. As the clouds are moving in from the ocean, they hit the Sierra Nevada, they start to rise over the Sierra Nevada, and you have the effect where more rain drops on the west side than it does on the east side, which is why Nevada is a desert, basically. And that's hugely important for determining where rainfall and runoff occur. Same thing with the Rocky Mountains relative to rainfall and runoff in the Colorado River system. Also a very important source of water supply for California. So in the next version of the IPCC report, their 5th assessment report, which will come out in 2013, notice we're doing a lot better on having smaller grid cells. Now, the trade-off on doing this is that these models are very large, very complex. They can only run on supercomputers, and running them can literally take weeks to a month to make a run. It's not a trivial thing. And in the research world, something that is not yet being used for the IPCC type work, but they're actually working on regional models. And this kind of looks like California now. You can see some mountain ranges instead of just a fuzzy box here and there. And you can see the desert down here. You can see the Central Valley. And we need this kind of level of resolution ultimately to be able to take information from a climate model, extract the precipitation component, and post-process it, and get something that we can use as input to the hydrologic models that we use when we work with water resources. Now, another thing about these climate models is the models don't all necessarily agree. The models do much better on temperature, generally, than they do on precipitation. And this is from the 2007 IPCC report. This is a particular emissions scenario I'll be talking about in a minute, and this is basically getting towards the end of the current century. This is temperature. And you notice there's this little sort of crosshatched pattern here. The crosshatching is where 90% or better of the models agree. So you can see this figure is pretty crosshatched. And what it's saying is that of these runs using using this particular emission scenario, the models are agreeing pretty darn well that it's going to be warmer. And one of the interesting things they're showing is the darker the color, the warmer. Well, one of the things the climate modelers are telling us is that this warming is expected to increase first in the Arctic, or the polar regions, I should say. And you notice that there has been a lot in the press about the observations of an increased melting of Arctic sea ice, for example. So observations are verifying what is suggested to be a trend going forward into the future. But on the other hand, same set of model runs, this is precipitation. And you notice we have a lot less crosshatching on this one. Models are much less consistent with respect to precipitation. And you see there's, some areas around here, up here, some areas. Definitely not nearly as widespread agreement. And some models are not necessarily consistent on the sign of the precipitation. Some say it'll be wetter, some say it will be drier. But as you can see from this, like in real estate, location is very important. One of the areas that a lot of the models agree on is warming and drying, or drying actually shown here, of the southwestern part of the United States. And they also agree that, up here, say, in the northern provinces of Canada, probably going to be wetter. And one shorthand term for talking about this in the climate modelers' world is they say the wet gets wetter, the dry gets drier. And if we look at where California is on here, we're kind of in this no man's land. Southern California might go sort of more towards the southwest, be drier, certainly be warmer. And who knows, the northern tier of California's counties might get a little wetter, but a lot of California is kind of that gray area in the middle. So this is something where if you're thinking about looking at the water resources impacts of this, you have to decide which models you place the most confidence in. And you don't just run one model, you run multiple models to look at results from a variety of models, and you also look at a variety of emission scenarios. This is a big uncertainty in looking at climate models, because when we're talking about emission scenarios now, we're not talking about modeling the physical behavior of a system, we're talking about modeling what people are going to be doing. And we all know that it's pretty darn hard to predict what people are going to do. They don't model as nicely as just physical science parameters. And so for purposes of the climate models, the IPCC has constructed a set of different emission scenarios, some that reflect essentially a projection of current conditions going forward, sort of a business as usual strategy, others that reflect varying levels of potential imposition of controls on greenhouse gas in the future, just to get a range of results for a sensitivity analysis purpose. This axis is global warming degrees centigrade. And when you look at some of the emissions scenarios, these gray boxes over on this side shows the entire range of potential results for that scenario with what they believe is the best value shown in that colored line. And you can see that's a very large range. So what you do when you look at the impacts of, say, these models and what they might say about California, not only do you have to look at multiple models, you have to look at multiple emissions scenarios. So you quickly have a lot of choices to look at and think about when you do this kind of exercise. Now let's talk about how we apply these uncertainties to a particular type of application, sea level rise. Well, what do we know about climate change and sea level rise? Well, there are several components to this problem. One component of sea level rise caused by climate change is thermal expansion of the ocean water. Just like when you boil a pot of water on the stove or in the microwave, water expands because it's getting hot. There's another component associated with melting of land-based ice. This would be ice on things like the Greenland ice sheet or the Antarctic ice sheet. It melts, will run off, end up in the water, so therefore sea level rise. That's global mean sea level rise. You have to adjust that to local conditions. One of the big local conditions of interest on the West Coast, throughout the West Coast, we're a very seismically active region. The reason for that is we're sitting on the edge of two tectonic plates that are rubbing up against each other and colliding. Parts of the West Coast are going up, parts of the West Coast are going down. And you can have additional local effects on top of that, such as subsidence due to extraction of fluids, oil and gas, for example, as has occurred in parts of the LA Basin historically. So you have to make those kind of local geographic adjustments. And then another impact of climate change is what the science community sometimes refers to in shorthand terms as the severe weather impact. And that is more severe storms, perhaps higher intensity precipitation, bigger wave heights. If you're designing a structure near the coast, you don't design for this mean sea level rise. You design for high tide with a storm on top of it, most likely, especially if it's a flood control structure. So that's something else that you need to think about. And this one here, the severe weather one, has a pretty significant level of uncertainty with it because it's still a very emerging area of science research. So let's talk about the cryosphere, for example. This picture is also stolen from IPCC. The cryosphere is what the science community refers to as everything that's frozen, shorthand term. But the point of this slide is really to point out that this is an ice sheet. And look how much mass of water is in that ice sheet compared to, for example, sea ice, which doesn't count anyway. It's already in the water, so melt the sea ice doesn't do much for you from a sea level rise standpoint. But, glaciers, your other land-based ice. One of the big reactions to the 2007 IPCC assessment report when it came out was many folks in the science community felt that report significantly underestimated the impacts, the amount of sea level rise in the future, because they didn't know how to really deal with this ice sheet issue. The thermal warming thing is something that you can extract from the climate models, but at the time they were publishing the 2007 report, there were new papers being written and published in the science journals pointing out, well, gee, look at how much warming and melting of sea ice in the Arctic we've already seen. New information was coming out. Some of you probably remember seeing about the breakup of a couple important large pieces of ice shelf. And this ice shelf, as it turns out, may have a buttressing effect against the land-based ice here that affects the rate at which the land-based ice can start to melt and move towards the ocean. And they also started to realize that other things were going on, such as meltwater getting underneath the ice sheet and sort of lubricating its flow and encouraging it to flow faster. And this is a whole area of science that's called ice sheet dynamics. And they realized that they really hadn't incorporated in their modeling because they didn't know that much about it yet. So that was a big uncertainty with the 2007 report, and that is something that's being looked at hard now in the current version of or what will be the next version of the assessment. So when we talk about some things in the research world that we're interested in knowing about, ice sheet dynamics is an obvious example. So that's one that has potentially a pretty significant impact on estimation of future sea level rise. Just to toss out a number for the sake of example, some programs around the San Francisco Bay Area are looking at a number of 55 inches by 2100 for planning purposes. That's the high number, but that's obviously still a pretty large number. And if you're, for example, the San Francisco airport, whose runways are sitting sort of right out there at the waterline right now, that's something that's of considerable interest to you. But some other areas, I talked about the climate models and the fact that the better you get the scale or the resolution of that, so you can actually see things like mountain ranges in the modeling, that's an important tool for improving the accuracy, we hope, of those models with respect to where precipitation changes might occur and where changes in runoff, from our perspective that we could model, would show up. Wanted to point out this picture here, if anyone recognizes it, is the Berlin Wall. Well, why do I have the Berlin Wall on the slide? And it relates to this first one. And this isn't limited just to climate change, but it's, this is an issue that existed before climate change existed, and that is being able to predict the weather or the climate further in the future better. In the science community, there literally has been for decades something like the Berlin Wall between the world of weather and the world of climate. Weather, as they say, is what you get. Climate is what you expect. Weather forecasts have a time domain of maybe out to 10 days at most. You don't see a weather forecast for a month, and that's because the models and the ability that they have to do forecasts simply won't let them go out that far. On the other hand, the climate scientists like to predict to 2100 or 2050, or they use very long time frames for these sort of global level science analyses. What we in the water community are really interested in, though, is, for example, it's October now. We would really like to know, is this water year going to be wet, dry, or average, because that would allow us to take different response actions in anticipation. We thought it was going to be dry, we might ramp up water transfers programs, water conservation programs. If we thought it would be wet, we'd start preparing for having more flood control response needs. And by the way, this is a plug that I will toss in. On November 17th, we, DWR, will be having our annual Winter Outlook Workshop, which will be webcast. And we bring together a panel of research scientists to give us their best crystal ball of what will the water year be like, wet, dry, or average. It's a really interesting discussion to listen to, so if you're interested, keep an eye on our website, and the information on how to hook up to the website will be published there. And last one I wanted to touch on a little bit was impacts of climate non-stationarity. There was a famous paper published a few years ago by an individual who used the title called Stationarity is Dead. And what he meant by that was the concept, because of climate change, the concept that you can use current climate conditions to predict the future doesn't work anymore. Well, this is a problem for those of us in the engineering and water management community, because that is exactly what our standard of practice is based on throughout this country and other countries as well, is we use statistical relationships and information based on the observed record to predict going forward. One of the major pitfalls of this, and this gets into that, getting back to the natural climate variability, is that we're working with a really short period of record. And there is huge uncertainty just within this historical record. Now, if you look at it from the perspective of geologic time, the Holocene time period, which we're in now, 11,000 years since the last major glaciations in the world, if you went back to the end of the Pleistocene and the early Holocene, you saw these guys, even down here in Southern California. There was a dwarf version of this guy living on the Channel Islands. You saw very different fauna, very different wetter, colder climate. This is within recent geologic time. Granted, 11,000 years or so is a long time period, but even if we went back to a more recent period of our recent past, people can do things like construct reconstructions of stream flow or precipitation from things like coring trees, for example. And by doing this, and by doing this, we can construct records of stream flow. This is the Colorado River, long-term average. And the point of this goes back to about 1500. We actually have a record of more than 1,000 years for the Colorado River. But just even in the, semi-recent past, there are droughts in the historical or the observed or prehistorical record that are much more severe than anything we've experienced in our modern period of maybe 100 years of data collection, less than that in some watersheds. So some of this stuff in the very recent past is really scary. And when we talk about another example of severe impacts that we're concerned about, and we talk about this adding this non-stationarity onto the effects of this major natural variability already, we just don't have the tools or a standard of practice to do that yet. So this is a major area of need for more information, for better research going forward. And because of the impacts of severe weather, we can lead to things such as needing new approaches for management. For example, if you're in a coastal area, there's been a lot of work going on recently about the impact of climate change on wave energy, wave heights, wave amplitude, storms hitting the coast. Well, that suggests that you probably need to think about taking a look at how you manage coastal development or erosion control projects along the coast, within a longer-term planning horizon, because this will start to be an issue. And also want to point out that the socioeconomic impacts, which are something that we don't think about so much, we work more on the physical science side, can be something that we really have to think hard about how to deal with. The picture here is Shishmaref. I don't know how many of you have heard of that, but in the climate world, it's a very famous example. There are a series of native villages in Alaska that are having to deal right now with impacts of climate change. Villages that were basically built on the edge of what is now the rapidly eroding coastal ice sheet, and they're literally falling into the ocean. And the state and federal government in Alaska are having to figure out how to relocate entire villages, where they relocate them to, how far in should they relocate them, and for those that are close to the edge but not quite this close, what kind of time frame should they think about for having to do this? These are all important kinds of questions that need to be looked at, and in the case of Alaska, they're sort of the first one to experience some of these. And in closing for my part of the presentation, I just want to point out that on the natural variability side, we don't really realize how severe some of our past just normal fluctuations in climate have been. This is Lake Tahoe. Now, many of you here have probably been to Lake Tahoe, big lake, very pretty, very deep. Researchers have found trees growing, rooted in place, they were growing, rooted in place, the stumps of trees rooted in place on the lake bed, underwater. Trees do not grow underwater. These trees were growing at a time when Lake Tahoe was not as high as it is in this picture. And some of these trees are significantly underwater, 30 feet, 40 feet. And they have dated them to back to 4,000 to 6,000 years ago, where there were some drought cycles in the Sierra Nevada, just due to natural variability, far more severe than anything we've seen in our 100, 150 years of record and observation in this area. So although we talk a lot about worrying about the impacts of climate change, of human-induced climate change, let's not forget that Mother Nature may have some other surprises in store for us also. So this is where I'm going to wrap up and let Mike take over, and I think we'll hold questions to the end for both presentations.
We'll talk about California's climate. But before we talk about what happens in the future, it's a good idea to find out where we're at now and what we've seen over the last century. So for my part of the talk, we'll just cover a few California facts because they're very important to the story. Discuss what I'll call present-day climate, which is essentially the past century, and then look at future climate and impacts. So, some nice features about California. We've 1,340 miles of coastline. It's about 75% of the Pacific coast for the lower 48 states. So we have a good exposure to the Pacific Ocean and the storms that come off said ocean. State about 800 miles long and an average width of only 250 miles, yet the state crosses 550 miles of longitude. Down here in LA, we are indeed east of Reno. So it's kind of an interesting concept to keep in mind. The land area, pretty good size. We're third behind Alaska and Texas, and you can see relative to the total U.S. area. All right, for elevation, our max elevation is Mount Whitney at 14,491 feet. Down in the southern Sierra, well, up in the Cascade Range, Mount Shasta, not too far behind it at 14,161 feet. Our lowest elevation down in Death Valley at minus 282 feet. Really interesting thing about it, Mount Whitney and Death Valley, only about 150 miles apart. So there's a really significant topographic feature in that part of the state. And then just for reference, many of the islands in the Sacramento-San Joaquin Delta lie about 20 feet below sea level. So, putting it up on a map, just a little topography, kind of looks like that. You see the rivers that drain the Central Valley. Here, this is the San Joaquin, Sacramento River, Klamath River there, Russian, Salinas River. We have the Southeast Deserts down here, Salton Sea. And you can see topography is a big part of California, and it plays a significant role in the variety and types of climates that we have here. So how does a climatologist take what we saw in the previous slide and group things together to give us a frame of reference? Well, over here on the right, we have the Department of Water Resources. We group things into hydrologic regions, and we have 10 of them. North Coast, Sacramento River, what we call the North Powhatan region, extends down past Lake Tahoe. And we have the San Joaquin Basin, San Francisco Bay Delta area, Central Coast, the Tuolumne Lake, or Tulare Lake Bed region here, South Coast, the Colorado River Desert, and the South Powhatan region. Now, our friends up at Western Region Climate Center have launched a product they call the California Climate Tracker. Now, what they did was they did an analysis of all the Cooperative Observer Weather Station data, and they came up with what they called their homogeneous regions in the state. And so there they have 13 of them. You can see there's some similarities between the two. They did choose to separate out the Sierra Nevada and separate out for the South Coastal region kind of the transverse mountain range that crosses there. We'll get more with the California Climate Tracker here in a little bit. Alrighty, so let's start working our way through different variables and look and see what we have in terms of present climate. So we'll start with temperature. So here is a product called a PRISM map of temperature. This is the maximum temperature for annual climatology. Climatology, to give a frame of reference, we pick a time period and we average over that time period. And our most current climatology is 1971 to 2000. Updated every decade. So here we are in 2010. Well, as we get into next year, we'll be updating and we'll have a new climatology coming out. That'll be 1981 to 2010. And these climatological regions affect everything from when they tell you what % of normal is to when you buy a seed packet and you look on the back and you see planting zones. They relate that to the most recent climatology. So you'll be seeing a new set of maps on your seed packets here. Anyway, for California, you can see we've got an amazing array of color here for an annual maximum temperature. We've got temperatures as warm as you can find anywhere in the continental U.S. and also some white temperatures that are about as cold as you can get anywhere in the U.S. And we do this over a pretty short distance. You compare that to other states out here in the plains where really not a lot of variability. And here we have for minimum temperatures, just to compare that. So there's kind of a spatial sense. Now, we're going to look at it through time. Now, what we do with these products, these are from the California Climate Tracker. Now, what they do is they take all the Weather Service cooperative observer stations in the state, and they compute an average of the maximum temperature for the whole year of all the stations, and that becomes one bar on the plot. So you're mashing a lot of information into one bar, so what that represents. Now what these are departures. So these are departures from a 1949 to 2005 base period. So here they've chosen a different reference to look at things, but it's rather interesting. So here we have statewide, and it's for a year-long period starting in October. Kind of consider October the start of our wet season. And so we can see that, a lot of cold bars here, cooler than average, kind of a spike of warm, and then things kind of oscillate around. But now we're starting to get more warm departures than cold. And the minimums, a little more consistent transition to where, back here you don't really see any warm bars. You see a few. Now we're getting hard-pressed to find any cool bars. So something's happening. All right, so let's focus a little closer. Remember the regions. So here we are in the South Coast region. And this is the same two plots. And this is what they look like. And you can see our last year here, actually a little cooler than average. So this past year, I think many of you would agree, this wasn't quite as warm. And even in the minimum temperatures, you can see the little bar down there. A little bit above average, but not quite what it had been earlier in the decade. Well, actually, if we go then for the Sierra Nevada region, where a lot of our water supply is from, you can see also this past year we had a pretty sizable cooler than average period in the maximum temperatures. But in the minimum temperatures, you can see this past year was the first time in a decade that we actually made it cooler than average. And even then, just barely. Whereas back in here, pretty sizable departures on the cooler than average side. So now let's talk about July. And this was called the new hottest month globally. And I find this entertaining because I had an interview in July from a Southern California radio station asking me about global cooling. Things here were a little different than the rest of the world. While many places around the world were setting all-time record highs, Here in the south coastal region, huge cool departure. The marine layer didn't give up. It's supposed to kind of cut back in June, give way to some sunshine in July, and it didn't do that. It remained deep, very prevalent. Interestingly enough, you go over the Mojave Desert region, so you just get over that transverse range. Look what happened for the same period. Much warmer than average. So a few weeks ago had, I guess you could call it summer compressed into a day down here. And there's some talk in the climatologist community, whoa, that came out of nowhere. And we said, well, not really. The deserts were actually quite warm. And in fact, while we were having temperatures here on the coast in July that were actually colder than January, so if it did feel cold to you, it was. In Las Vegas, not too far away, up the road, they had their hottest July on record for every day of July. They were over 100 degrees for a maximum. So a very short distance, a lot can happen, and that's the story of California. As Jeanine said, location is hugely important in what happens. And for summer, statewide, all right, so let's get to precip here. Again, a PRISM, a precip map, you can see a lot of red in California. California's a pretty dry state overall. Mountains, really what get us our precipitation. And in some cases, quite a bit. Up here on the north coast, you're looking at well over 100 inches. Whereas down in here in the desert southeast, it can go a year and not rain. That's not unheard of. So, again, massive variability. And here's a really interesting study that was done at Scripps. And what they did was they took all these little dots to represent a cooperative observer site from the Weather Service. And they said, well, let's look at, in 3 days, how many stations received over 30 centimeters of precipitation, and how many times did that happen, and that color-coded the dots. Well, here on the Gulf Coast, you see quite a bit of green. That's in the 5 to 10 region, a couple of hot spots there, and maybe a few that may be from thunderstorms. But probably hurricane activity defines those. Now let's come over to California. And you say, wow, look at that. And we've got spots in the North Coast, probably the Mount Shasta area, this part in the Feather River Basin, 20 to 25 days. Topography matters in California when it comes to rainfall. Even here in Southern California, you get up in those mountain ranges that stick up, get in the way of the coastal moisture coming in. It makes a huge difference. Now, if we look at, again, with the climate tracker, and we look at statewide precipitation over the century, you'd have to stare at that really hard to try and convince yourself you see a trend there. There really isn't. We do see, this dry 20-year period here. Jeanine was saying, well, you don't have to look too far back to find some scary periods. Well, right here is 1921 to 1940. For the state of California, it was a pretty sizable drought. We can even do that for here. So this is in California. You'll hear something that we use in the department called the CalFIS, Aid Station Index for the Sacramento River. 8 rain gauges that span the Sacramento Basin. This gives us a good feel for what precip's going on in our major water-bearing reservoirs for the state. And here I broke it into 1921 to 1960. The average was 48 inches. 1961 to 2000, 52 and a half. So in the latter half of the century, we actually got more rain. Best year, 88 and a half inches in 1 year. Now contrast that, 1924, 17.1. Year-to-year variability here is fantastic. And so it looks like this. Here's 1924. When, boy, that would be quite scary to deal with. Here in 76, 77, many of you probably remember the adventures that drought caused. You can see that's a sizable hole, pretty much only rivaled by 1924. 86 to 93 drought in our most recent adventures here. All right, snowpack. What we have here with the Department of Water Resources, we kind of break our snowpack regions into 3 areas. The north, pretty much think of the Feather River north and over into the Trinity Alps. And what we have here is this is our best year, 82, 83. We had well over 200% of what we expected effect, or our average snowpack that year. And it lasted. Look at this. We're over here in late May, and it hadn't started melting yet. April 1st is considered the traditional peak. If you look at the average line, which is kind of the shaded in blue. We really peak about April 1st, and then we expect the melt to happen. You can see here in 76, 77, you really almost can't say we even had a snowpack. They hardly had a chance. Some of these are the more recent ones, 2007, 2008, 2005, 2006. Central Sierra is pretty much from then the Feather River Basin down through Yosemite, and south of Yosemite down through the Kern River is the south. April 1st, we had an average snowpack. And we thought, okay, we made it to April 1st, we have an average snowpack. But by the time we got through July, and April through July is when we kind of expect our snow to melt and we fill our reservoirs, we only had 60% of the runoff. And the water manager said, wait. April 1st, he said we had an average snowpack. Where'd the water go? Well, turns out that it started snowing and the ground got really cold, but the soil underneath was really dry. There really wasn't any precip to kind of wet up the soil underneath. So we had a snowpack, but it's sitting on really dry soils. Now, Mother Nature's going to take her share before she releases the rest into the river for us. And so that's something that we have to keep in mind. And here's kind of a time series through time from 1975 of the snowpack, and you can see how big 82, 83 was. And as I mentioned, in terms of runoff, here's the Sacramento River. This is by months, and you can look at the size in terms of million acre feet of water running off, and let's come back here. And we see that we kind of peak broadly across the winter all the way through the spring. So this is a mixed system. We get our rain that produces runoff, and we have then the snowmelt season. And we really have broad peak. But you can see kind of an interesting thing split, breaking the time series around 1955-56. Latter half of the century, we're seeing more runoff happening in December, January, February, and March, less happening in April, May, June, and July. San Joaquin Basin. Boy, this looks a little different. Higher mountain range in the San Joaquin. Peak runoffs in May. This is a snowmelt-driven basin. But you can still see the same trends happening. In April, May, and June, decreasing. Wintertime, you're seeing increases. Jeanine mentioned extreme events. This is the Feather River and the American River. And these are the annual maximum flows. This is going into Folsom. This is going into Warrenville. And you can see prior to the construction of Folsom Dam, this was the hydrology and extremes they dealt with. The size of the reservoir, figure out how big the spillway to make. And that's why they built the reservoir. Well, this is then what they're asked to operate to. You're seeing peaks happening fairly frequently that never happened when it was designed. Well, this leads to what we call now the Folsom Modifications Project, which is to try and get the reservoir to fit more of this than what it was designed for. And this gets to what Jeanine pointed out. The way we did business in the past was using the history. This is only going to be a more regular occurrence for us, and we're going to have to start thinking about what do we do with that as an engineer. As you mentioned, sea level rise. And here we have the Golden Gate time series. And so you have the annual value, and then we have a 19-year running mean. Anybody want to guess why we use 19 years? That's kind of an odd choice to have as a running mean. But 19 years happens to be the period in which the Earth, Sun, and Moon go through in terms of their orbital cycle. And that has a lot to do with tides. And so you'll see things referred to the 19-year mean. Well, you can see that 19-year mean creeping up. But as Jeanine said, it's those individual event years that are going to come and haunt you. And people say, well, what's climate change going to look like? Well, let's look here, where 82, 83, pretty strong El Nino. You're looking, from that 19-year mean, you're looking at almost a foot of where the sea level is about a foot higher. And all the adventures that we had with storm damage in that year and that. You have to start wrapping your head around, that's average. Things pile on top of it from there. So it could be some interesting times. So now we get to talk actually about the future here. And this was a quick summary of all the things we talked about. Increased air temperature, precip may increase or decrease. Depends on where you are, which model. But we have a feeling that we're going to see more rain than snow. Snow's going to melt earlier, get more runoff earlier in the year, more compressed into the wintertime. Changes the timing and the amount of river flows. It's going to have a huge impact on the ecology. It's also going to have a huge impact on the water resource systems operations. We set up our reservoirs and everything, again, based on history. Well, history's changing, and so we're going to have to deal with that. And, oh, by the way, sea level is on its way up, too, which is going to impact how we do things. So here's a slide from Scripps, and Dan and Jeanine had shown this, showing pretty consistently we've got an expectation that temperatures are going to be rising. Here's our expectation for precipitation. And if all you see are a bunch of scribbly lines, then you are right. There's a lot of uncertainty here. This is history, though. A lot of uncertainty. And this helps us out. This is what we've had to deal with as a state. Enormous variability. Remember with the 8-station index, 17 inches for a low, 89 for a high. Okay, if you're managing with that kind of variability as it exists now, that can help you deal with what you're dealing with out here. So there is some good thoughts to be had there. Now we get to the extreme events. Again, we talked about extreme weather and topography being so important. Well, in a global climate model, it's hard to get that topography to be there. And, okay, well, if we're already having to guess that we're going to have to deal with extremes, one of the first things we have to do is figure out, okay, if the model can't show the topography that's really important to that precipitation process, what can we get out of the climate model that might inform us what's happening to our extreme events? Alrighty, so a word that's going to become part of California's lexicon is atmospheric river. And NOAA scientists found out that 90% of the poleward transport of water vapor happens in these thin, concentrated bands. And they said, boy, that looks kind of like a river. Let's call it an atmospheric river. All right, that looks pretty good. Well, we see here in the tropics, in this plot, the reds, purples, is atmospheric water vapor. There's a lot of it in the tropics. And occasionally you have disturbances that go through the tropics, and this is a depiction where you kind of get a bubble of this really high intensity water vapor. And you see then storm tracks coming along and kind of drawing into that, drawing them up, and occasionally it draws it up and boom, delivers it to California. We could start looking at some of these circulation patterns that create this in the global climate model. Because, again, this is a Pacific-wide phenomenon that these set up on. And you can start tracking this kind of information to try and determine how changes in this might happen with its delivery to California. Those are our extreme events. Those are our big floods. That might give us a feel for what's going on. They did a study with a watershed model. And they said, well, Feather River watershed is the main watershed for the State Water Project. And they said, well, what happens if we start raising temperature? It's just a sensitivity study. Raise the temperature, see what happens with the snowpack and the snow melt. And this was their base case. They had a little over 25 inches of snow melt. Well, they increase it. We start seeing it decrease and by a 3 or 4 degrees Celsius increase. Okay, if you operate a reservoir by reserving a flood space, anticipating that, boy, come spring, we'll have snow melt, and that'll fill it back up, and we'll be okay. Okay, maybe not. But we have one facility that in the wintertime we bring down to protect us from the winter floods. So this is going to be one of the fundamental challenges that we'll have to deal with. And you can see some of the numbers here. 1 degree Celsius, 15% decrease in snowmelt, 60% by the time you get 4 degrees. And they say 4 degrees Celsius, the mean annual runoff shifts from mid-April all the way back to mid-March. So you're going to have to try and start catching your water supply in March when you can still have a big storm hit the basin. And we do different exercises, and it's a anomalous big storm that happens in early May. By May, they're thinking, I'm filling this reservoir, try and top it off, peak it out just right, hit the lip, and then I can deliver all that through the summer. Life is good. Okay, at the beginning of May, if all of a sudden I have to start thinking midwinter flood control operations, I'm going to dump water I'm not getting back. And that's the scenario that we're going to find ourselves in here. And here's another, some projections the department's done working with the sea level rise. And this is in feet, but kept going at the same pace it'd be here. So we do see there's some acceleration that's expected based on the climate projections. So just because we're seeing something happen at some rate doesn't mean that's going to be what continues. So some take-home points. California's climate is highly variable. Just fantastic, which is both good and bad. Future climate impacts going to be location dependent. And we saw kind of some of that this summer. Boy, whether you were on the coast or in Las Vegas, not too far away, but you had very different Julys. And the impacts are hugely important to water resources. This is going to be one of the greatest challenges to deal with. Yet the uncertainty and projections are high. So you're going to try and plan for things changing on you, but you're not really sure how much and when. And so that's going to keep things interesting. So I think that the fundamental take-home point for engineers and the public alike is know your watershed. Know where you live, know what happens there. And for California, this means not only the watershed you live, but also the watershed where you get your water. Questions?
Is there any relationship between sea level rise and groundwater getting polluted the same way that the salinity is increasing in the delta?
That from just the historical perspective. There was a report that our department published in the early 1950s that talked about saltwater intrusion in coastal groundwater basins in California, and you could literally look at a map of California, and there was a dot along every place on the coast where there was a significant city, because the phenomena of seawater intrusion into coastal groundwater basins was already occurring then because of pumping. And in fact, in Southern California, because that issue got rapidly so significant with respect to possibly precluding future use of the basin, at least from an economic standpoint, that was why you saw most of the basins here get adjudicated in a court process or similar kind of process very early. So if you exacerbate the potential for migration of seawater to occur inland by rising sea level, yes, that does make the problem worse, although frankly at the rates of pumping in some of the unmanaged basins, I think in the near term that will surpass the effects of sea level rise. Down here in many of your managed basins, because the basins are now highly managed, it becomes less of an issue. You have the tools in place to manage the basin. You may have to shift your management regime somewhat.
Assuming there's going to be more runoff as opposed to snowmelt, and it's going to appear more in big batches, what plans do you have to catch and save more of that water?
You want to talk about your operation studies?
Yes. Right now, the department is launching a project with the grand title of System Reoperation. And the idea here is to look at a feasibility study of, with the given infrastructure that you have in place and your expectations of both current climate variability and future climate, what changes can you make in how you do things to try and create what they call integrated water management. Try and combine the management of both floods and water supply because you see this greater overlap of the two occurring. So it's a study that's just getting on its feet right now, and I think over the next several years that will become more and more something the department will be continuing to investigate.
It's probably worthwhile pointing out, too, that it's this is definitely one of those location is everything kind of issues. If you compare the Sierra Nevada watersheds with the Colorado River system, the Colorado River system has, from an operational standpoint, probably much less vulnerability to climate change because it has so much storage. On the Colorado River system, the ratio of storage to average annual runoff is 4-to-1. Because the river was highly variable, it was recognized when they were designing facilities in that system that there was an awful lot of year-to-year variability in flow. So the fact that you have that storage capability and the ability to manage it is really helpful. Go to the Sierra Nevada watersheds, and it's almost the reciprocal of that. You don't have anything like a 4-to-1 ratio. If anything, it's more like a 1-to-4, a quarter or a half, meaning that I like to use the term with the Sierra Nevada watersheds, it's kind of like a put-and-take fishery. Catch and release fishery. You catch the fish, you put it right back in. Well, the way we manage our Sierra Nevada watersheds, because of this trade-off for flood control that Mike was alluding to and water supply, we're not holding that water for very long, so to speak. We're just kind of slowing it down because we don't have a lot of storage to manage there. And this is something that makes the challenges of the Sierra Nevada watersheds, say by the end of the century, will be really interesting. Some of the studies that have been done with respect to the effect of climate change in the Sierra Nevada talk about, for example, an 80% loss of snowpack, more or less, by the end of the century. Well, the snowpack currently is acting like another reservoir up there. And as we lose that sort of natural storage capability in that snowpack, the challenge of trying to manage both flood and water supply becomes very difficult. Well, actually, there's a good product out in the web that you could find on the California Climate Change portal, which shows you some nice graphics on where sea level rise could be under different time frames. But what it doesn't really show you as well is the fact that lots of California has cliffs. So, if you've got a cliff right next to the ocean, a foot or two of sea level rise is not a big issue for you. Where you would be looking at is those lower lying areas along the coast. Ahem, did anyone mention Long Beach, for example, or Los Angeles, where you don't have that, and also areas where there has been historical subsidence due to things like oil and gas extraction. Oh my, that wouldn't be Long Beach now, would it? So, this part of Southern California is an example of an area which is less protected, let's say, than Mendocino, where you have these huge sea cliffs right next to the ocean.
It seems like on the State Water Project in the Sacramento Delta area, they're having a really hard time right now managing flows in order to provide the water for ag in urban areas and for the environment. Will they have to, how are they going to manage it in this kind of a future that you're talking about, even like 20 years out or 50 years out? Can they continue to try and achieve those shared goals of water supply and environmental protection?
Well, this is really a public policy issue, not a climate change issue. And as many of you know who follow the newspapers, what to do about the Bay Delta, how to balance the resources, restore the ecosystem, try and meet water needs, is a hugely complicated challenge that people have been working on since the 1950s. And public policy has yet to gel behind a particular or settle on a particular approach, although there's a process going forward now called the Bay Delta Conservation Plan, which would be, in essence, to, in compliance with the Federal Endangered Species Act and the California Endangered Species Act, gets what's called a Habitat Conservation Plan and a Natural Communities Conservation Plan as a way of protecting a number of species broadly, while at the same time trying to continue with the operation and maintenance of the water project. So that's a public policy question with respect to just existing facilities and infrastructure. And I'm sure you've all heard the planning work that's going on about looking at ways to, for example, improve the reliability of supplies to Southern California through some kind of conveyance structure through the Delta, whether it's conveyance among Delta islands, whether it's a canal, whether it's a tunnel, which has been talked about in the newspaper lately. But set that aside for a minute, and let's think about the geomorphology, if you will, of that area, or the risk to sea level rise. Most of you probably know, and Mike alluded to the fact that the Delta is composed of all of these islands, many of which are very far below sea level. These islands were constructed for the purposes of agricultural development beginning around the time of the gold rush. The levees that protect them, many of which have failed over the years, were literally built up with farmers with their scrapers with teams of mules and horses. They're not engineered levees. Many of them are on very poorly founded peat soils. And as a lot of folks have pointed out, one major earthquake could radically change the geography of the delta as we know it today. The delta would like to go back to being a salt marsh. And you know what they say about not messing with Mother Nature. So we are, in essence, if we try to, reflecting the fact that we now have 38 million people in California and a completely altered environment from what existed in the early 1800s. So if we try to stabilize this area in the delta, deal with these hugely fragile levees, Mother Nature could really throw us a wrench, 20 years out, 30 years out, if we had a major storm that caused several key levees to fail, or if we had an earthquake. So the delta is, just from a standpoint of geomorphology, a very difficult area to work in. Add climate change impacts on top of that, more severe storms, higher flood risk, becomes a pretty scary thought. Well, as a state water agency, we just deal with the freshwater side, so we do not deal with ocean resources. There are others in the federal agencies who have a focus on ocean acidification, and in fact, a lot of research has been published in that area. There were a couple of very interesting leading papers recently published by some NOAA scientists talking about the potential impacts of ocean acidification on the entire marine food chain, because as you know, it's not just what happens to some of the, potentially might happen to some of the more charismatic species at the top of the food chain, but what effects filter up. And one of the spillover effects, so to speak, might be what happens to some of the anadromous fish that we have to manage for their freshwater side of their life cycle, salmon to be particular. If ocean conditions, because of changes in the ocean food web, significantly change how well salmon do when they're in the ocean, that has implications for us from a water management standpoint, potentially with respect to how they're managed on the freshwater side.
As engineers, do you anticipate that there would be any need for an increase in the next 50 years over the amount of storage that there is in the Sierras? Since you mentioned that there's very much a put and take effort, or effect rather, in the Sierras as opposed to the Colorado River Aqueduct.
One of the issues about the Sierras is that many of the best dam sites are already taken, so to speak. There have been studies of enlarging capacity of existing reservoirs like Shasta Lake, for example, but it really comes down to a question of feasibility in a variety of ways: financial feasibility, environmental feasibility, et cetera, and the ability to get a project through the regulatory conditions that we have and build it. Certainly, more storage is good. Some of that storage, there's certainly a lot of potential for developing more managed storage in California's groundwater basins. This is kind of a glass half full, half empty sort of thing. In many places in California, Central Valley, for example, southern end of the Central Valley, we have some hugely overdrafted groundwater basins. Well, that's the bad news, but the good news is they're kind of empty. So, you could use those as one form of storage. But part of the problem with the Sierra is just that we have so many people in the Central Valley, for example, living in floodplains, and so much development that has already been constructed that really limits your ability to what you can do in terms of managing floods. Mike can tell you about some of the channel capacity problems in the San Joaquin River system, for example, that even if we could dump a whole bunch of water from the dams up there, we can't manage it downstream because we'd be flooding out a lot of the communities in the San Joaquin Valley. So it's a complicated issue.
If you have a flood, can you recharge into the groundwater fast enough, or is that a slower process that groundwater recharge isn't feasible for immediate flood control?
Well, I don't want to be taking all the questions. Okay.
I can do this one. It depends. Again, location is important in this case because geology is important. Different soil types that you have, some lend themselves to fairly quick recharge of the groundwater system, others slow. either way, you need land set aside that can be inundated for an extended period of time that you can divert the floodwaters into. As Jeanine mentioned, we've had a lot of development in the Central Valley, so locations where you can find that are rather limited. And I think that becomes more of the challenge, is finding those suitable locations that don't have houses on top of them.
And for example, you have sort of an extreme example of that here in the Los Angeles coastal plain area. The county of Los Angeles was really very forward-thinking very early on in the last century by developing a lot of local groundwater storage in conjunction with the smaller, relatively small debris dams that they have in some of the mountains around here, the San Gabriels, for example. And there are actually some fairly large groundwater recharge facilities, like the Rio Hondo facility, for example, that the Los Angeles County has. But I mean, a place as urbanized as this area is, you simply can't build enough new capacity. You couldn't afford to buy out the land from the industrial and urban uses to build new facilities. But there's actually a fair amount of built capacity here in Los Angeles County, but of course one would always like to have more.
We've built a lot of flood control dams in Southern California, for instance, Whittier Narrows. To my knowledge, that's never been closed. Can you close them and start using it to recharge the groundwater?
Well, as you probably know, there's been a lot of coverage of Whittier Narrows in the papers recently regarding some dam safety issues associated with it, in response to the fact that some local agencies would like to do just that. And actually, this is not just a California issue, but throughout much of the western U.S., people are taking a second look at some of these Corps of Engineer dams that were built only for flood control and saying, well, is it possible to get a little additional storage of water supply in these dams? And a lot of that depends on the design of the dam itself and its location. A number of these core flood control dams, because they were built to control floods, to knock off a peak, to temporarily slow the movement of water down a channel, they're pretty leaky, so to speak. Not a problem from a dam safety standpoint, but not exactly ideal from a water storage perspective. So there are some dams in the western U.S. where people, the local agency who partnered with the Corps on the flood control side, has been able to go through a planning process and design something that provides at least some small level of storage. And the Prado Basin is a good example in this region. But there are some other western states that are looking at some attempts to significantly increase storage where the physical setting of the dam works out for that.
At least in those cases, you have some of the land behind them already set aside.
Yeah.
Well, Jeanine and Mike, thank you very much for coming here tonight.